Hello everyone and welcome to my presentation. Thank you all for attending today. My name is Pieter de Bod and I am a senior engineer specializing in HVAC systems design for the last 20 years, and I'd like to share with you very interesting information on using thermal solar collectors in HVAC applications. In this presentation we will look at the reasons why using thermal solar collectors is really an attractive alternative to conventional HVAC systems. And we'll review the different technologies, efficiencies, applications, economics, and design guidelines. By way of introduction, I'd like to make you all aware that in 2018, the International Energy Agency published a 92-page article which they called The Future of Cooling. In the foreword, it says that the world faces a looming cold crunch, and using air conditioners and electric fans to stay cool accounts for nearly 20% of the total electricity in buildings around the world today, and this trend is set to grow. The answer lies first and foremost in improving the efficiency of air conditioner systems. Also in the executive summary, it says that since 1990, the annual sales of air conditionings more than tripled to 135 million units per annum, of which about half of that is from just two countries, China and USA. The rising demand for space cooling and heating is already putting enormous strain on electricity systems in many countries, as well as driving up emissions. So how can we address this problem? And that is solar energy. Solar collectors provide free heating and cooling. So, free heat can be converted into cooling, and we call that active solar cooling. The pie chart below shows the percentage heating and cooling requirements is approximately 40% in a typical commercial building, and solar cooling and heating systems have the ability to reduce that figure. Active solar cooling has the advantage of the coincidence of solar radiation with the cooling demand. That basically means that in most cases the solar energy is the highest when the cooling demand is the highest, typically between noon and mid-afternoon. The active solar market grows approximately 40% per annum. It is still a niche market, but costs are reducing. The worldwide awareness of global warming and zero carbon buildings stimulates the need for low energy buildings and heating cooling systems. There are two types of solar collectors. The first is the photovoltaic or PV panels to generate free electricity, and secondly, thermal solar collectors to generate free heat. This presentation specifically focuses on solar thermal collectors to generate free heat. Did you know that the world's first solar cooling system was displayed at the World Exhibition in Paris in 1878, where they used an absorption chiller with a parabolic reflector, as you can see in the picture on the right. They used ammonia and water as refrigerants to make ice blocks, and unfortunately commercial systems only followed 100 years later. Now let's look at different solar collector technologies. The most common and cheapest type of thermal solar collector is the flat plate collector, or FPC. Heat from sunlight is transferred to a liquid that flows through pipes inside the collector. The liquid is typically glycol, which is a mixture of water and antifreeze agent, and that is used to prevent freezing due to frost or snow. The cold liquid enters the bottom and the hot liquid exits at the top. The flat plate collector construction is fairly simple and consists of an insulation base, copper tubes, absorber plate and a glass cover. The underside of the collector is insulated to avoid thermal heat loss. The air gap between the tube and the absorber plate also acts as an insulator and to reduce the heat loss. The absorber sheet is coated with a spectrally selective material to improve the absorptivity of sunlight energy and to improve efficiency. Flat plate collectors typically have a liquid out temperature of around 100 degrees C or 212 degrees Fahrenheit. There are many different configurations for FPC systems, but the most common configuration is to circulate the hot liquid from the solar collector through the hot water tank. An heat exchanger is used. The hot liquid from the solar collector does not mix with the hot water in the tank. FPCs is simple and proven technology with a good cost-performance ratio and is readily available. There are no moving parts and is easy to install on the roof and ground surfaces. The next type of solar collector is called the evacuated tube solar collector, or the ETC, which is an improved version of the flat plate collectors with regards to thermal losses. Here the absorber sheet is encased in a glass tube from which the air has been evacuated. The vacuum in the glass tube results in less heat being lost to the environment and thus a greater efficiency. Evacuated tube collectors are commercially available in two different models: direct flow collectors on the left and indirect flow or heat pipe type on the right. In the direct flow type, primary liquid flows in the copper tubes inside the glass wall. With the indirect type, the primary liquid does not flow through the tube but flows through a manifold where there is a metal bulb that becomes extremely hot. The bulb is heated by a secondary fluid which does not come in contact with the primary liquid. ETCs typically have a liquid out temperature of around 200 degrees C or 392 degrees Fahrenheit, and more expensive than flat plate collectors. ETC technology is proven technology, and the collectors are readily available. There are no moving parts in these collectors. It's also important to note that the individual tubes are lightweight, easy to install, and can be replaced easily if damaged. This picture shows the various components inside a ETC. Notice the bulb on the end that gets extremely hot when in the sun. The application of the evacuated tube collectors is very similar to that of the flat plate collectors, except that it pushes out a far higher temperature. The picture on the left shows a flat plate solar panel and an evacuated tube perpendicular to the sun's rays. On the right hand, it shows the sun at an angle. One of the reasons why evacuated tube collectors are more efficient than flat panel collectors is because the tubes are almost always perpendicular to the sunlight, which is not the case for flat plate solar panels that reflect some of the sun rays. I just want to mention a third technology which is called hot air collectors, where air flows through individual channels and is warmed up by the sun. These collectors typically have a glass cover with a backsheet housing and a thermal insulation just like flat plate collectors. This collector can reach air temperatures up to 120 degrees C or 240 degrees Fahrenheit. This technology is not commonly used worldwide, most probably because of the low heat capacity and density of air versus water. Water is 784 times more denser than air. When multiple hot air collectors are connected together with an air filter and a fan, the hot air can be blown into a space and the temperature can be controlled with a thermostat. The next type of solar collector is called the concentrating solar panels, or CSP. I'm really excited to share this information with you because their high thermal efficiency makes them very suitable in applications of solar cooling systems. There are three types: the compound parabolic concentrating collector, or CPC, the parabolic trough collectors, or PTC, and lastly the linear Fresnel reflector, or LFR. The compound parabolic concentrating collector uses an evacuated tube like we've seen before, but with an additional parabolic reflector mounted below the evacuated tube. This directs solar radiation onto all the sides, including the underside of the collector. Compared to a standard evacuated tube, the CPC tube have a much higher efficiency and therefore can supply a much higher heat. CPC tubes require more space on the roof due to the reflector space and requires high maintenance for cleaning of the reflectors. The picture on the right shows an additional glass cover over the reflectors to avoid dust collection on the reflector itself. The heat generated by the CPC is typically provided to either an absorption chiller to provide chilled water to a building or industrial process, or the heat can go through an heat exchanger to provide hot water or steam. Another type of concentrating solar panel is called the parabolic trough collector, or PTC, which uses a trough-shaped parabolic mirror to reflect the sun onto the absorber tube. The concentration ratio of the mirror is much higher than for CPC collectors, in the order of 80 to 80 times higher. The concentrated radiation results in high supply temperatures of up to 400 degrees C or 752 degrees Fahrenheit. This is an example of a small PTC with a footprint of 46 square meters or 495 square foot. It can collect approximately 270 kilowatt hours or 920,000 BTUs on a clear day using 10-hour sunlight. There is a water tube running in the center, and the length of the trough is the focus point of the solar radiation. Water is pumped through the receiver tube and is heated as it passes through the tube. The parabolic trough collector can collect solar energy up to 10 hours a day compared to 6 hours of day for regular flat plate collectors. Several sections can be ganged up together for more heat. Most PTCs maximize harvesting of sunlight by tracking the sun using a drive motor, as illustrated in this picture. It is very important to note that PTCs require direct radiation because diffused radiation cannot be reflected by the mirrors onto the tube. PTCs do not work well in areas with high diffusion radiation like the tropics. This map shows the areas that are most suitable for PTCs. The areas highlighted in orange have an excellent suitability for CSP plants, while areas highlighted in blue is unsuitable. These pictures shows more examples of PTC installations, ranging from large installations on the left to smaller installations on the roofs on the right. PTCs can generate heat up to 400 degrees C or 752 degrees Fahrenheit, and ideal to drive large district cooling and heating plants, where the heat will energize absorption chillers to generate chilled water or ice making, or to provide heating for water or steam as shown in the picture on the left. The heat is also sufficient to generate electricity. The last type of concentrating solar collector is called the linear Fresnel reflector, or LFR. This collector is named after French physician Augustin Jean Fresnel, who invented the reflective Fresnel lens that uses multiple flat mirror strips to concentrate the sun's radiation onto a secondary reflector. Note that the mirrors are all at different angles but all pointing to the focal line above. The secondary reflector has a parabolic shape that collects the rays from the mirrors and redirects them onto the absorber tube. The secondary reflector is really necessary because the mirror strips do not concentrate the light themselves, and without that, some of the reflected light would miss the absorber tube. The advantage of a LFR is the use of multiple small flat mirror strips that are much easier and cheaper to manufacture. The simple support frame of the mirrors are also located closer to the ground, and the weight is less and have less wind load on them. Note that more area is required compared to other CSP collectors due to spaces between the mirrors. The absorber tube of the collector is stationary, while the only moving parts are the mirrors, which follow the sun using one-axis tracking. As mentioned, the relative simplicity and lightweight of the LFR allows it to be easily installed on flat roofs. This photo was taken of South Africa's first LFR, and the hot water is used to drive an absorption chiller that generates 6 degrees Celsius chilled water or 42 degrees Fahrenheit, feeding a mission-critical facility or data center. This client is MTN, which is equivalent to AT&T. They are South Africa's second largest telecom company. They are pioneers of renewable and alternative HVAC systems in Africa. I'm also proud to say that I was the designer for Africa's first tri-generation plant that integrated into the same system. This is a photo of me back in 2010 when I visited the linear Fresnel reflector solar cooling plant at the Engineering School of Civil in Spain. The system is composed of a double effect absorption chiller delivering 174 kilowatt or 593,000 BTUs per hour cooling capacity and powered by a 352 square meter or 3,800 square foot LFR. The solar energy presented 75% of the total heat input to the absorption chiller and was topped up by the heat from natural gas. This picture shows how the LFR can be used to generate chilled water, hot water, or steam. There's a company in California that commercially manufactures micro LFRs, and they use the same technology as utility scale LFRs. It has been designed purposely for rooftop integration. The micro LFR is low profile, lightweight, and has no external moving parts and simple to install and maintain. They claim it generates temperatures up to 200 degrees Celsius or 400 degrees Fahrenheit. As can be seen on the graph, this micro LFR outperforms many other collectors. That company claims that their micro LFR generates 6,400 BTUs per hour using an area of 45 square feet and weighing just under 5 pounds per square foot. They also claim that their micro LFR generates 400 tons of heating using 480 units occupying just under 26,000 square feet floor area. To summarize, the LFR has a higher supply temperature than a standard evacuated tube collector or a CPC. The flat mirrors are cheaper than curved reflectors of parabolic troughs. The stationary absorber tubes make the installation simpler and can be easily installed on flat surfaces like roofs and open areas. However, the LFR has a lower efficiency due to the secondary reflector compared to a parabolic trough. It requires regular cleaning of mirrors and tubes and requires direct normal irradiation. Another type of solar collector is the photovoltaic thermal collector or PVT, which is a hybrid collector that generates simultaneous power and thermal heat. It comprises of a flat absorber for heat and electricity collection. Typically, the thermal heat absorber below absorbs the heat from the PV cells to cool it and allows the PV to operate at a much higher efficiency and generate more power than standard PV panels. As expected, the thermal heat output of the PVT is less than a standard flat panel collector. Let's look at basic terminology. The efficiency of a collector is the ratio between the useful heat from the collector divided by the solar energy falling onto the collector's surface. It is used for instantaneous power calculations and annual performance simulations. This table illustrates the general collector efficiency for different types of solar collectors. On the vertical axis shows the collector efficiency, and on the horizontal axis indicates the difference between the mean collector and the ambient temperature. It can be seen that the linear Fresnel collector efficiency is very uniform. See the bright green line. On the other hand, the efficiency of a flat plate single glazed collector deteriorates quickly as the temperature difference between the mean collector and the ambient temperature increases. Another basic terminology is the concentration ratio, which is the aperture area divided by the absorber area. The concentration ratio for non-CSP collectors is 1, while the ratio for parabolic trough collector is the highest, followed by the linear Fresnel reflector. This graph summarizes the heat output for each collector as well as the possible applications. Starting from the top, the parabolic trough and linear Fresnel collector can provide sufficient heat to generate chilled water using the absorption chiller, where the chilled water can be used in cooling systems. The heat can also be used for industrial process heat or space heating. The thermal heat output from evacuated tubes, CPC collectors, and high-performance flat plate collectors are lower but can be used for the same application. Regular flat plate collectors or PVTs are good for domestic water heating and space heating, where air collectors is good for space heating only. You may recognize this slide from earlier. I would like to discuss the solar cooling chiller itself, which can be either an absorption chiller or adsorption chiller or a desiccant evaporative cooling device or DEC. Let's look at absorption chillers, which are available in single effect, double effect or triple effect. The refrigerants that are used in absorption chillers are typically water and lithium bromide, which is like a salt, or water and ammonia. These chillers have been commercially available for the last 6 decades, and the cooling output can vary anything from 10 kilowatt to 23,000 kilowatt, which is 2.8 tons to 6,500 tons, and minus 30 to 5 degrees C, which is minus 21 to 41 degrees Fahrenheit. The thermal COP is the heating energy input in BTUs per hour divided by the cooling energy output in BTUs per hour. Please note that the thermal COP should not be confused with the standard COP used for conventional electrical chillers, which is in the range of between 2 and maybe 16. The standard COP for an absorption chiller is in excess of 125. Adsorption chillers use silica gel as refrigerant and generates chilled water at 5 degrees C or 41 degrees Fahrenheit and is commercially available in capacities between 2.8 to 140 ton. These are examples of absorption chillers. I visited the world's largest absorption chiller manufacturers in China and also in Slovenia on behalf of my clients for the various projects in South Africa. The factory tests were successful and these chillers were shipped to South Africa following my inspection. This illustrates the functioning of an absorption chiller where there are many thermodynamic processes at play. And note that the main energy input to the absorption chiller is the free heat generated by the solar collector. This process is too elaborate to discuss in this forum, and I will leave it for another time. This is an adsorption chiller which uses silica gel as the refrigerant. It is quite magic. Hot water in, cold water out. There are two types of desiccant evaporative cooling or DEC systems: solid air systems or liquid desiccant systems. The DEC use free heat from the solar collector in the cooling and heating process. There are many variations, but the principle is the same. The free heat from the solar collector indirectly removes the humidity from the outside air and utilizes cooling from evaporative coolers to cool down the space or heat up the space. The system uses very little electrical energy. A heat recovery wheel as well as a desiccant wheel with silica gel is used in this process as well. This is an example of a desiccant wheel on the left and a close-up of the holes, or flutes as they call it, in the wheel surface on the right. These wheels rotate slowly at approximately 12 to 16 revolutions per minute and can transfer sensible or latent heat or both. Another variation of desiccant evaporative cooling is the liquid systems, which are very similar to the air systems. However, they use a hygroscopic solution to attract water from the air and gets diluted and is regenerated afterwards using the free heat from the solar collector. I know it sounds complicated, but there's a diagram that illustrates the principle. Thermal storage of heating or cooling is a very important component of solar cooling systems. It is important to differentiate between heat storage and cool storage. Although storage is not generally necessary for overall system operation, it provides important advantages, which are: number one, decoupling of solar yield from the load profile during periods of high solar irradiation and low cool demand. 2. It allows nighttime operation without sun. Heat or cool storing during the day can be used in periods without sunshine. 3. Cloud buffering periods of intermittent cloud cover during the day can be breached in order to maintain continuous system operation. 4. Robust system control potential temperature fluctuations caused by changing ambient conditions can be balanced out by the storage tank. And 5. Provision for heat for other purposes. These are examples of small-scale hot water storage tanks, which is typically less than 2,640 gallons. These are examples of large-scale hot water storage tank. The picture on the left is an example of a pre-manufactured, insulated, pressureless hot water storage tank assembled on site. The picture on the right is a 12,000 gallon insulated, pressureless hot water storage tank that's also under construction. The design temperature of the water inside the tank is 208 degrees Fahrenheit, which serves as a heat source for a heating water for a district heating plant. Another type of thermal storage is by making use of phase change materials, or PCMs. PCMs melt when heat is added to the tank and they solidify when heat is taken out of the tank. One of the main advantages of a phase change material is that it takes up approximately 8 times less space than a conventional hot water storage system. Common PCMs for heat storage in solar cooling applications are paraffins, fatty acids, and hydrated salts. This table gives an overview of the physical properties. Chilled water storage. It is possible to store chilled water, but it has a very low storage density compared to hot water storage, at around 7 kilowatt hours per cubic meter. Ice storage only requires approximately 20% of the volume of chilled water tanks and require a supply temperature of -3 degrees C or 26.6 degrees Fahrenheit. This technology is very commercialized. Free heat from solar collectors drive an ammonia absorption chiller to generate the temperature as low as -30 degrees C or -22 degrees Fahrenheit. These are examples of ice storage tanks. Eutectic saltwater storage is another alternative to ice storage, and it requires only 20% of the water volume of a typical chilled water tank. However, the freezing point is raised to 6 to 8 degrees Celsius or 42 to 46 degrees Fahrenheit by adding hydrated salts to water. The water-salt mixture is encapsulated in small plastic balls, and the system requires a supply temperature of 6 degrees or 42 degrees chilled water. These type of systems are also commercialized. The free heat from the solar collectors drive a lithium bromide absorption chiller to generate the chilled water for these tanks. Eutectic saltwater storage is used at the world-famous Petronas Twin Towers in Malaysia. I had the privilege to visit this building back in 2005. Insulated storage tank holds the eutectic saltwater balls and the chilled water. The phase change of the freezing or melting results in storage density comparable to pure ice. When it comes to designing a solar cooling system, there are many different design approaches and methods. This is a condensed overview of a rather complex design process. This manual method can be used as a first design in feasibility studies as well as for a preliminary cost assessment. The methodology starts off with the building itself and a sustainable building design. Once optimized, determine the cooling and heating loads. Then, using the climate data, determine the weather data and radiation parameters. Once that is done, determine the chiller plant size and any chilled or ice water storage. Then calculate the solar heat required and size of the heat storage capacity. Design the plant control system, and lastly perform the annual system simulations, and also determine for any backup energy needs and auxiliary power consumption of the solar cooling system. Economic feasibility. This flowchart is one method to calculate the economic feasibility for a solar cooling system. This diagram shows the method and steps required to utilize the net present value method. Each individual step needs to be completed in order shown. In most cases, we have to present the method to evaluate whether a solar cooling system has a lower or a higher lifetime cost than a standard conventional air conditioning system of a similar size. The technical design as well as the economic viability are interlocked with each other. Changing one will have effect on the other. If this is the case, an iterative calculation process will have to be followed. The best market for a solar cooling system are mainly determined by the following factors: the solar resource, or the sun, the climate zones and seasonal variations, the energy costs in the area, as well as the building type and application. A solar cooling system requires good solar irradiation conditions. Typically, this solar resource map is used for initially assessing this parameter. It is interesting to note that not all locations on Earth with high global horizontal irradiation numbers are suitable for solar cooling. For example, the tropics have high cloud cover and therefore diffused radiation, and not suitable for solar thermal collectors that requires direct radiation. The seasonal variations within a climate zone have a strong influence on the performance of a solar cooling system. A solar cooling system will provide the best economic performance if the solar array can be utilized as much as possible. So from the point of view of economic feasibility, it is imperative to have either high annual cooling loads or combined annual heating and cooling loads. Energy cost is also a very important factor when economic feasibility is calculated. The local cost of energy, electricity, natural gas and water determine the operation cost of the heating and cooling system. This applies to both standard and solar-driven systems. Therefore, the higher the cost of utilities at a given location, the higher the savings that can be made by a solar cooling system. Well, folks, this concludes my presentation. I hope you enjoyed learning more about solar air conditioning systems, and as you can see, I'm very passionate about energy efficient air conditioning systems like this. I really believe it's time to seriously rethink our design philosophy and to adjust to the environmental challenges we face today. Please reach out to me if you need any more information.